In this video, we're going to be looking at some slightly more advanced techniques in integrating hyperbolic functions or integrating with hyperbolic functions. So have a look at this. We've got the integral of x sec squared x. So pause and have a think what your intuition is about how to do this. Well, whenever we have the product of two very different types of functions, like x, which is a polynomial, and then sec squared x, a hyperbolic function, it's often the case that integration by parts is the useful way of doing it. And when we do integration by parts, we're looking for one of the products. It should be something which we would be very useful to differentiate, and one which we're okay integrating. And we do have that because x is very helpful to differentiate because it just goes. And sec squared x, well, that is the integral, or that is, sorry, the derivative of tanh x. So we can integrate that to tanh x. That means that my u can be x, and it means my v dash can be sec squared x. That's really helpful because u dash is 1 and v is tanh x. So this is actually going to be fairly straightforward because we integrate using parts and we get x tanh x minus the integral of v u dash, which is just the integral of tanh x. We saw a couple of videos back that the integral of tanh x is ln cosh x. And the reason for that is that tanh is sine over cosh, and sine is the derivative of cosh. So ln cosh x plus c. And we are done. Of course, we always in these options have the option to express these hyperbolic functions in terms of e's, but I think this is by far the neatest way of representing our answer here. Okay, let's have a go at this. The integral of r cosh x. So the integral of the inverse hyperbolic function. So maybe there's some temptation here to think that, to use the fact that r cosh is ln of x plus the square root of x squared minus 1. But this is going to be no fun to integrate at all. So I really would not recommend that technique. Instead, I'm going to suggest using the technique that I would use to integrate arc cos x from trig or arc sin x. When you're integrating those, a really clever technique is to use integration by parts and to imagine that this was 1 times r cosh x. And we're going to set our u as the r cosh x because that's going to be okay to differentiate. And we're going to set our v dash to be 1, meaning our v is x. So what do we get here? We get uv, which is x r cosh x, minus the integral of vu dash. Well, we're going to need the integral of r cosh x. Once again, that's one, if you forget, that you can find in your formula book. The integral, the derivative of r cosh x is 1 over root x squared minus 1. So I put that here, 1 over root x squared minus 1. And now I can do this. So that's v u dash, so that's x over root x squared minus 1. Now this integral is not too bad because I can use reverse chain rule. And maybe it's useful to notice that this is the same as x times x squared minus 1 to the power of minus a half. And then what you can see is that x is, well, it's a multiple of the derivative of what's inside this bracket, which means that what got differentiated? Well, it must have been that bracket raised to a higher power. So it's going to be something like x squared minus 1 to the power of a half. Let's do a quick check in our heads. If I was differentiating this, I'd get a half times the bracket to the power of that minus 1. And then I'd multiply by the derivative of what's inside the bracket, which is 2x, giving me a half times 2x on here, which is just x. So actually, this is perfect as it is. And that actually means we are done. And there's the answer. If we want, we can write it a little bit prettier. So r cosh x minus the square root of x squared minus 1 plus c. And there's the integral of r cosh x. And a similar technique is going to work for integrating r shine and r tangent as well. So give those a go as well. All right, let's have one area between curves problems. Now, I think you've seen enough now to pause and have a go at this yourself. So definitely do that if you've already done so, then hopefully you've already answered it. All right, the diagram shows the curves y equals 5 cosh x and 7 plus sine x. We want to find the region, the area of the shaded region. Okay, so overall, this is going to involve taking the integral of the function which is on top minus the function which is underneath between the two limits. So there's a few things we need to do. We'll need to do that integral. We'll need to figure out which function is actually on top, and we'll need to find the intersection points. Now, we know from our knowledge of what the curves look like that cosh looks like that and shine looks like that. So you can kind of see pretty quickly that the red curve here on top is the 7 plus sine x. You could also reason that the y-intercept of 7 plus sine x is 7 plus 0, and the y-intercept of 5 cosh x is 5. So that gives us our sort of order. It's going to be the integral of the curve on top, 7 plus sine x, minus the curve below, which is 5 cosh x, and our remaining job is to find the limits here. So that's when the curves are equal to each other. So that's when 5 cosh x is equal to 7 plus sine x. So solving these, you basically have to just convert everything into e's. So that's 5 e to the x plus e to the minus x over 2 equals 7 plus e to the x minus e to the minus x over 2. So let's double everything and expand. So multiplying by 2, I get a 14 here, and then the divide by 2 just goes, leaving me with e to the x minus e to the minus x. Here, doubling gets rid of that 2, leaving me with 5 e to the x plus 5 e to the minus x. Let's get all of this onto one side. So that'll be 4 e to the x minus 14 and plus 6 e to the minus x equals 0. Multiply through by e to the x to reveal the disguised quadratic. 4 e to the 2x minus 14 e to the x plus 6 equals 0. Go ahead and solve that, and we get e to the x equals 3, or a half. And that's good that we have two possible solutions, because we wanted two possible x values here and here. It means that x is ln 3 or ln a half. So that's going to be useful. I'll just leave those like that. So those are my limits. Ln half is the smaller one, ln 3 is the bigger one, and now I can do my integration. So we've got 7x. The integral of sine is cosh, so that's cosh x minus 5 sine x. And all of that between ln a half and ln 3. So what do we get? Well, subbing in 3, I get 7 times ln 3, I get 7 ln 3. Then for these you can just do them on the calculator. Find your cosh button, that's totally fine. And you can just sub in cosh of ln 3 and discover that's 5/3. I know I haven't been doing that recently, just to sort of show the method of subbing in, but we're totally allowed to do that. Okay, and then 5 sine of ln 3. So I get my sine button of ln 3 is 4/3 times 5 is 20 over 3. So minus 20 over 3. And now I'm going to be subbing in ln of a half. So that's 7 ln of a half. I'll probably convert that into ln 2 in a moment. Then we've got cosh of ln a half, and that's 5 over 4. And then sine of ln a half, which is minus 3/4, but times that by minus 5, and it's plus 15 over 4. And all I'm left to do is neaten this up. So what have we got? We've got 7 ln 3. Now, it's minus 7 ln a half, but ln half is minus ln 2, so that's plus 7 ln 2. And then I'll just call all of these fractions. So 5 thirds, minus 20 thirds, minus 5 over 4, minus 15 over 4 is minus 10. And there's my answer. And of course I could factorise out the 7 and call that ln 6, but I think this looks totally fine as an answer. Okay, that's all. I'll see you in the next video.